Good evening, everyone. Um, I hope everyone can hear me. First of all, I would like to thank Shorajan for inviting me for this wonderful event. And I would like to say Happy Earth Day to everyone attending this impressive and amazing event today. Thanks, Arizujan, for the introduction. As Ariz said, my name is Hadis. I'm an assistant professor at Chemical Engineering Department at Ryerson University, and also the vice chair of Chemical Institute of Canada in Energy Division part. So today I would like just to briefly give you the outline what I'm going to talk about. First, I will talk about global challenges and climate change, and then about renewable energy and need for an uninterruptible clean power. Then why electrochemistry, the science of electrochemistry is so important to achieve that uninterruptible clean power. Then I will briefly talk about some of our research strategy at my research group at Ryerson called NLEAD, or Nano Engineering Laboratory for Energy and Environmental Technologies. And I end my talk with some conclusion and the perspective we have to further achieve our goals. So as all of you know, like we're dealing with the climate change, global warming, and one of the major contributors to our global warming is the release of greenhouse gases, among which the carbon dioxide level is getting very high in the air now. According to the climate NASA website, the most recent update about 416 ppm, that is about milligram per liters, is the level of carbon dioxide in over 650,000 years. And because of the rising of the greenhouse gases in our atmosphere, so the global temperature has been rising about 2.1 degrees of Fahrenheit, or 1.80 degrees C of degree of centigrade since 1880. And because our globe is getting warmer, the major ices are melting down on the earth, and the sea level has risen nearly 8 inches over the past 100 years. Because of that, as you are aware, like since 2016, like we entered, like all the nations, all the countries entered a new agreement called Paris Climate Change Agreement. Then the goal was limiting global warming, preferably to 1.5 degrees C compared to the pre-industrial levels. How they're going to do that? Basically, to achieve this long-term temperature goal, countries are going to reach a global peaking of greenhouse gases as soon as possible. So everyone, they will gonna this year, like 2021, most of countries that released their plans, including Canada, that how they're going to do that. And the outcome, the expected outcome is by 2030, like zero carbon solutions could be competitive, like in sectors representing over 70% of the global emissions. Now, what's the role of Canada over here? So government of Canada basically expects to reduce its greenhouse gases emission by 30% by 2030 and achieve a net zero emissions economy by 2050. In order to achieve that, the government has committed about $3 billion investment to establish a net zero accelerator fund to helping like the industries that are the major emitters to reduce their emissions, and the research and development of many research institutes, the academic institutes and universities to achieve this goal. So there is a very high potential of R&D opportunities for Canadian universities, industries, and national research institutions. So what's the answer? What's the answer to like replacing the the fossil fuels or those resources that are causing these emissions? The answer for this to reach a safer environment for future generation is and slowing down the climate change is in renewable energy technologies that have zero carbon footprints on our environment. That includes solar, wind, hydro, bioenergy, nuclear, and geothermal. But in order how to utilize this, we need a system that we can have an uninterruptible clean power. As you're aware, like there is now lots of researchers or plans going on to create a smart grid, like utilizing all of these renewables and connect it to our grid for different applications from our house loads, transportations, and portables. But what's the challenge over here? The major challenge is what methods we can use to store this energy and efficiently convert it to power upon need. Because these are like natural resources, and we have to, for the time that the natural resource is not available, we have to store the energy, harvest that energy, and use it upon need in our smart grids, in electric vehicles, or any other applications we need power. Electrochemistry science here comes to help us because electrochemistry is basically a science that studies the production of electricity from chemical changes, or reverse. We can produce useful chemicals like clean hydrogen fuel that occur due to the flow of the electrical current. So basically, to put it in a simple word, electrochemistry is about the movement of free electrons and how we can use that. The examples are, as you have seen, lots of solar panels now being applied on the rooftops. Like I know some, I live in downtown Toronto, like some of the buildings are incorporating them. Many farms are using it. Basically, those panels, the science behind it is based on electrochemistry called photoelectrochemical panels. So it harvests the energy of the solar. Another example is the most popular example are batteries that we have been using them for a long time, and now they're trending, especially for electric vehicles. So what happens? We can use these batteries to store the energy, for instance, in the daylight from the sun, and then in the nighttime that the sun goes down or the wind stops for the wind turbines, we can use that stored energy to get power from. And the last but not least, another famous example that how we can harvest those energies are the use of water electrolysis and fuel cells. What does it mean? Water electrolysis are basically a system that we use the energy from the sun to split water to its components. As we know, water is composed of hydrogen and oxygen. So by splitting it to hydrogen and oxygen, we can use the energy of the hydrogen as the fuel and get the power from by using fuel cells, which is a reverse reaction of electrolyzers. However, similar to any other emerging technologies, new technologies, there are still some challenges to overcome to efficiently commercialize these technologies, make them reliable, and reach our target based on the assigned date by the governments and the Paris Agreement. So these challenges are basically cost, is because due to the comprising materials of these systems, it's the basically the weight. Some of them are still in a heavy weight, especially for instance for electric vehicles. We prefer to have lightweight transportation, or even for portables. Another is the energy and power density. So energy density means how much energy they can store, the capacity, and power density means how fast we can get that energy or give it to the system. Stability and lifetime, so we need them to be run for a long time, so it's important to prolong their lifetime. And last but not the least, basically the last two are safety and system integration. So safety again lies in the compartments of the materials, and the system integration means, as I showed you, like the loop that we're looking for, like how these different systems can be connected and provide us power. Based on this, basically the main target or the main focus of the research is defined in my research group based on this introduction. So in order to address some of these listed challenges at NLEAT, we're focusing on developing smart materials that are efficient, multifunctional, strong, cost-effective, and lightweight. For different applications, clean technologies. One is clean energy and another one an environmental remediation. But I would like to stick with the clean energy as is the core topic of my today's speech for you. So for the advanced materials for electrochemical power, basically, I would like to give you a simple representation how the general compartments of these electrochemical cells look like. So basically, they have like two electrodes called anode and cathode. These are separated by another type of layer called electrolyte. That could be liquid or solid. So I'm just trying to show you what are the basic roles of each part. So anode and cathode at each side are responsible of how much energy, how large the energy or capacitance is inside the electrochemical cell. And here the middle one, the electrolyte, is responsible how fast we can get the energy from or charge in terms of batteries charges. So I know all of you want to have, for instance, your cell phones charged much faster. So again, here the electrolyte has the role. The better electrolyte, the faster charging process you can get from. So all of these electrochemical systems that I introduced to you, they can be used for a wide range of applications, for large power applications like households and transportation to our portables that are now, we cannot disconnect it from them from our everyday life. Our strategy to make these compartments and address those challenges that I listed for you is nano engineering of these materials, using the tools of the nanotechnology and nanomaterials to address those. So I know most of you may have heard about carbon nanotubes, graphene, wonder materials. So we're trying to work with analogous materials like those, like CNTs or carbon nanotubes, or graphene, or another analogous materials is called white graphene we're working on. We're trying to use these wonderful properties they can have because of their atomic thickness in different directions. So harvest their high surface area, they're tuning their electrical properties and their high strength in terms of mechanical and thermal strength to utilize them in electrochemical system, energy storage and conversion systems. Some of the I'm just showing some pictures of what we have done so far or achieved. For instance, in terms of electrolyte, we succeeded to make a very high functional solid electrolyte that help us to have very dense and lightweight electrochemical energy storage and conversion system. So these solid electrolytes that we're developing, they have the capability like liquid electrolytes. Close to that to transport the charges very fast to get the high power densities. In terms of the electrodes, we also succeeded to make very flexible and strong electrodes. They have high electron conductivity, high energy capacitance. So that means we can get higher energy density from. This is just a demonstration that I would like to show you. One of the very packed, sorry, I have two screens. I'm just looking for the play. Okay. So as you can see, this is just a demonstration showing a wind turbine and how the packed, dense battery we made, the film, could power this. So we're trying actually to scale up this now and get for like a stack of these and higher to provide power for high power required systems. In conclusion, so as I mentioned, for these electrochemical cells, two important things in terms of performance: high power density. So far, our group succeeded to make it 14 times higher than the commercial solid electrolytes like Nafion in the market. We achieved high energy density with a very thin film, so promising for the more lightweight energy storage systems, about 3 times higher. And we could also successfully assemble these, making electrochemicals. So we made water electrolysis, use these materials for water electrolysis, for batteries, for supercapacitors, for fuel cells so far. And we could reach, for instance, in terms of supercapacitors, about 100,000 cycles, which is outperforming anything reported so far by retaining 90% of the capacitance. However, still, there are lots of things, challenges remaining to be resolved. One of them are how we can integrate all of these different systems to make that nice loop and cycle of using our resources, producing energy, and again, everything back to the environment. So we still need to increase the real-time electricity capabilities and reliabilities by working on the comprising materials of this system. I also would like to acknowledge my great team, my PhD students, masters, and postdoc fellow for their great job in this regard, and also all the funding agencies and collaborators that have supported these projects so far. And I would be happy to answer your questions in the chat box or afterwards in the linking. Thank you very much.